Welcome to this explainer, where we are embarking on a massive, zooming journey today. We're going to start way out, looking at the everyday human psychology of problem solving, and then we're going to dive deeper and deeper until we literally reach the microscopic electrical pulses firing inside a computer chip. If you've ever wondered how your abstract thoughts translate into the physical operations of a machine, you are in the exact right place. Let's get into it.
Here is our roadmap for today. 1. Thinking like a computer. 2. Programming versus coding. 3. A programmer's daily routine. And 4. How code controls hardware.
Section 1. Thinking like a computer. To truly understand software, we first have to understand ourselves. We need to look at how we organize our thoughts long before our fingers ever touch a keyboard. So, the crucial question here is asking ourselves, how do we actually solve complex problems? What is happening in our brains when we tackle a multifaceted issue, even if there isn't a computer anywhere in the room? Well, this foundational concept is known as computational thinking. Barefoot computing brilliantly illustrates this idea. They show us that these super technical sounding skills are actually deeply human. They apply just as much to organizing a chaotic family vacation or figuring out the logistics of cooking a 3-course meal as they do to building software. It's really all about taking a structured approach to the world around you. It's kind of fascinating how these 6 concepts break down everyday actions into the exact logical frameworks that computers use to function. Think about algorithms. That's literally just following a recipe step by step. Decomposition is breaking a massive headache into bite-sized chunks, like packing your bags before planning the driving route. Abstraction is a really cool one. It's about stripping away the noise. Think of a subway map. It completely ignores the winding city streets above and just shows you the straight lines and stops you need. Add in pattern recognition, evaluation for making judgments, and logic to predict facts, and boom! Master these 6 concepts, and you are a computational thinker, whether you ever write a single line of software or not. Section 2. Programming versus coding. Let's see how this builds into actual industry disciplines, because you've definitely heard these 2 terms thrown around interchangeably, but in the tech world, they represent entirely different scopes of work. Programming is the big picture. It's the architectural strategy. Before a single line of syntax is typed, a programmer is planning the structure of the app, using management tools like Trello, they're designing user interfaces, and establishing the overarching logic that will make the whole software ecosystem actually function. Coding, on the flip side, is the highly specific, tactical act of taking those planned instructions and translating them into a language the machine can read. This is where you're hitting the keyboard, typing out specific syntax in Python, Java, C++, whatever it is. The coder acts as the vital translator between human intention and machine execution. When we put them side by side, the distinction is crystal clear. Coding means knowing the syntax, living in text editors, and aiming for a specific immediate output, like whipping up a quick script to turn a PDF into an audiobook. Programming, however, demands a deep knowledge of overarching algorithms and modeling frameworks. The programmer's end result isn't just a quick script, it's a complete, maintained software system that users are going to interact with every single day. Moving on to Section 3, a programmer's daily routine. Now that we know what they actually do, let's humanize the industry a bit. What does a typical day feel like for a software creator? Looking at these insights, it's a highly structured, super dynamic day. You kick things off with stand-up meetings to align the team. Then comes the mid-morning deep work, those intense headphones-on sessions where the heavy problem-solving actually happens. After lunch, the afternoon pivots to high collaboration, reviewing teammates' code and brainstorming new features. Finally, the day wraps up with rigorous testing and documentation, just to ensure everything built that day holds up under pressure. And this reality totally shatters the myth of the isolated, basement-dwelling coder. While the physical act of coding is solitary, collaboration is absolutely massive in this job. Modern programming requires tremendous teamwork, empathy, communication, and adaptability. You are constantly talking with designers, project managers, and quality assurance testers to bring a product to life. Finally, Section 4, how code controls hardware. Let's take that ultimate plunge, zooming all the way down to the microscopic level to see how those typed characters from a developer's mid-morning coding session physically control a computer chip. This flow right here reveals the true magic of computing. It starts when a human types a simple word like print in a text editor. From there, a program called a compiler translates that human word into assembly code that is specific to the hardware's architecture.
That assembly code then becomes binary, just a massive sequence of zeros and ones. And here is where it gets crazy. Those zeros and ones literally represent the absence or presence of digital electrical voltages. Those exact voltages are fed into microscopic transistors and logic gates inside the chip to physically execute the command. Human thought literally transforms into physical electricity. How cool is that?
Now, when developers write code that gets this close to the hardware, what we call low-level programming, there are some major trade-offs. On the pro side, you get immense direct control. You optimize performance and memory, which is life or death essential for time-critical applications, like the software running a car's anti-lock brakes or a pacemaker. But look at the cons. The complexity skyrockets. You have to thoroughly understand both the software and the physical constraints of the device itself. Plus, it opens up severe security risks, like buffer overflow attacks, where bad data spills over into hardware memory it definitely shouldn't access. It is incredibly powerful, but very hard to debug and costly to maintain. As we wrap up this explainer, I want you to take a second and think about your own problem-solving style. Look back at those 6 concepts of computational thinking. If you love getting into the weeds of syntax and translating ideas into tight strips, you might be a natural coder. But if you thrive on designing overarching systems, plotting out the logic, and orchestrating how all the puzzle pieces fit together, you might just be a programmer. The truth is, we need both to make the modern world run. So where do your skills fit into this fascinating journey from human thought to digital voltage? Keep exploring that, and we'll see you in the next explainer.